Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be continuing to do AMC 10 and 12 preparation before the upcoming exams in November. We are 5 weeks now away from the 10A and 12A test date on November 10th, and there's still time to prep, so check out our blog post for tips and tricks to help you prepare for that test as well. Now, let's jump into our problems then here. So our first problem is from the 2018 10B number 23. And we're looking for integer solutions to this equation involving LCMs and GCDs. So we have a mix here of some number theory, of course some algebra, different things going on in this case as well. So we want to keep in mind that we have these positive integer ordered pairs. So that is something we want to always keep in mind. Little hints for how we might want to think about stuff and how that might help us solve equations there. Now, this equation is weird. We have the least common multiple, we have the GCD, we have the product of the numbers in this case. And those three things should make us think of a pretty useful fact, right? If we're given numbers, we should know how to find the GCD, LCM, prime factorizations, different stuff like that there. But there's also a pretty helpful relationship. So if we make a substitution here, we're going to solve a different equation here. So x is the LCM of A and B, and y is the the GCD of A and B. So we have our two expressions here that we are working with. Now, when we see this there, right, okay, we have 20x plus 12y on the right-hand side. Well, what about the left-hand side? And here's where this important relationship actually helps. Well, x times y, GCD times the LCM, hey, this is in fact equal to the product of A and B. So this piece of information, this is actually going to be very helpful when we're solving this expression. Because now we can rewrite everything in terms of x and y. Notice that that is still then different variables. We have x and y at the end. We're going to have to turn this back into A's and B's and think about that as well. But let me rewrite this and do a little rearranging here. So let's keep our x, y on the left-hand side. Let's move over the 20x and the 12y. And let's put the negative 63 on the other side. Now, there's different names for this. I like calling this completing the rectangle because we want to factor this expression. Because we're looking for integer solutions, that means, oh, if we factor it, some nice things can happen there. So we factor this. Well, pretty good thing to try would be xy. Then we have first times first is x times y there. Now, how are we going to get a minus 20x? Well, then outsides x times negative 20 will give us that negative 20x. X minus 12, then minus 12 times y will give us the negative 12y, right? And of course, then that needs a positive 240 right here. So of course, we can't just add that for free. We need to add 240 on the other side. So we get x minus 12 times y minus 20 is 177. And again, remember we're dealing with integers. We're dealing with a little mix of number theory here. So it might be helpful and will be helpful to write this out in terms of its prime factorization as well. So we have x minus 20 times y minus 20 is 3 times 59 here. Now, why is this going to be helpful? Well, we know a couple of things. So we know that the LCM is bigger than the GCD. So right off the bat, we actually know that x is bigger than y. So if we think about this as two products, x is bigger than y, and their product needs to be 177, which is 3 times 59. Well, one way to do this is we could have 59 times 3, of course. Or we could have another possibility here of just the kind of boring one, but 177 times 1. So we could deal with these separately then here in terms of some cases. So we have one case here of one solution so far, and then we have another solution here that we consider separately in a moment. So let's do that off to the side then here. So in our first scenario, let's do a little bit in our head here. X minus 12 is 59 in this case. So adding 12, we get that x is 59 plus 12, 71, right? This is supposed to be the LCM. Y is 3 plus 20, 23. Now, can the GCD be 23 and the LCM be 71 of two numbers there? Think about this a little bit and you'll see pretty quickly that this is impossible, right? The LCM needs to be a product of the GCD. Think about, oh, the product, right? The LCM is the product divided by the GCD, right? We have some nice relationships there. Clearly, if we have two numbers and we're looking at their smallest shared factor, a multiple of both of those numbers is a multiple of that shared factor. So that's not going to work here. So what about the other case here? So in the other case, we have that x is 170 plus 12, so 189. And y is going to be 21 in this case. Now, 189 is 21 times 9. So this works out in this scenario. So this one seemingly is okay. But let's just pause a moment and remind ourselves that we still need to solve for A and B, right? So x is the LCM, y is the GCD in this case. So how can we have numbers here where their least common multiple is 189 and their greatest common divisor is 21? Well, it's not too hard to see here. Well, we need them to both be multiples of 21 in this scenario, right? Without sharing any other factors. But then 21 times 9, that's just adding 3s. So one possibility here is we have A and B is 189 and 21, right? Think about this. Could we have something like 63? Well, if we had 189 and 63, then the GCD would be 63 and not 21, right? So this is what we have there. Or we can have that this is equal to the opposite. Remember, we're looking for solutions of A and B. So the order matters. Those are two different variables. So our answer is B in this case. We have two solutions at the end here for A and B. So make the substitution, solve for x and y, but don't forget we need to go back and find our final answer in terms of A's and B's in this setup. Okay, so let's look at one more here. This is a AMC 12B question about complex numbers in this scenario. And we're going to want to start kind of looking at a picture and starting to think about things as well. Now, a lot of these, right, especially a question like this, immediately when you read complex numbers on a plane, we're doing squares of stuff, you really want to think about these numbers in polar form. So if we take a look at our number here, right, so we have our omega in this case, we want to write that in polar form here. So in rectangular form, right, the x value is -1/2, then we have √3/2. This is making us think of multiples of, right, 30 and stuff like that there, right? So what we have then in this case is, and if you want to use polar form or kind of rectangular form, however you want to do this there, right, this is going to be cis of, how about we do degrees just to help visualize it a little bit easier, cis of 120 degrees in this case, right? Cosine of 120 is -1/2. Sine of 120 is √3/2. So this works out then there. So let's draw this now and start to draw this, or at least start visualizing this on our complex plane. Now, first of all, notice here that this is 1 times cis of 120. The magnitude of this is 1. That's pretty helpful, and that's actually going to make things a little bit nicer in this case, because that's telling us that our entire thing is living on the unit circle. So let's draw out a unit circle here, a little bit lighter color just so we can draw over it later, but that is our unit circle. So omega is there, omega squared is there, everything we have is like that in this case. Now, I want to draw out our point. So if we draw our point here, roughly at a 120-degree angle, this point right here about is going to be omega. And of course, I could write this as 1 omega. And the reason I'm doing that is, right, and let's do this verbally, that actually tells us that this line here, right, this line from the origin out to 1 times omega, right, this is all the values. I'm going to erase this in a moment, but this is all of our values b times omega. So if it's 0 times omega, we're at the origin, and then as b goes from 0 to 1, we're traveling on this line, or on this vector if you like, up to the point omega at the end. So we get all of those points along the way. So just cleaning it up, right, that's giving us our b omega there. So let me highlight that portion of this too. Now, let's maybe go backwards a second. We could do a same thing pretty clearly for just a. So we have a, or a times 1, right? This point right here is the point 1. And so then any combination from the origin out to 1 is going to be giving us our values there, right? So we have these values here for a, and then for a times omega, we have these values here. Now, we could start looking at combinations from this point, but let's just get our omega squared out here too. So omega squared, and this is the real advantage of polar form. When we square something in polar form, the magnitude squares. Well, there's no magnitude, it's still on the unit circle, and the argument or angle will double. So this is cis of 240 degrees in this case. So now we have our omega squared down here. And likewise, if we then look at something between 0 and 1 times that, we are going to be on a line from the origin to that point there. So these three spokes or things, however you want to think about it, are giving us our kind of values here from A, B times omega, and C times omega. We don't have any shape yet. There's no area yet here. And this is where we need to start thinking about combining some of these expressions there. Now, this is really, we're doing some vector addition stuff here, but I think it's good to think about the extreme cases. So let's think about stuff like, for example, I'm going to put this in a second, where would 1 plus omega be? Now, couple of ways to do this. You could do this with rectangular form, negative 1/2 plus 1/2 I root 3. That becomes 1/2 plus 1/2 I root 3. So from there, we can see that this point is going to be somewhere up here. But I want you to start thinking about these in terms of our combinations. So if we go to the point 1, and then we add omega to it, right? This is where really, if you know about vectors, this is something that's pretty obvious here. But what we're really doing then is still moving along that same kind of line in that case. So we're moving up here to this point 1 plus omega there. We can copy over that omega, and that's allowing us to go up to the left at this 30-degree angle from north, if you like. And notice that we could do that same thing from omega squared. So this kind of over here, right, is going to give us our point in this case, right, the edge case then. So this point here is omega plus omega squared. And again, hopefully it's clear that by changing the A's and B's or B's and C's, we can get every point along these lines as well. Now, what if we do the same thing for 1, right? Of course, if we add in the other direction, this is 1 plus omega there. If we do this on the bottom, we can actually go over as well. So our kind of final point here, drawing isn't perfect, so let me fix this a tiny bit here, or fudge this a little bit here if you like, right? This would be our point 1 plus omega squared. So of course then that means that if we add in these other lines for omega squared, we're getting really this hexagon shape at the end. And it shouldn't take too long to convince yourself that actually any point inside this hexagon is possible. So anything inside our hexagon here is going to be possible because of the range of values of A, B, and C. So, right, the whole hexagon, the area equals the area of the hexagon. So that is our area of S in this scenario. And let's not spend too much time on this. This should hopefully be something people are comfortable with. There are 6 equilateral triangles that make up this hexagon. Each of those equilateral triangles has a side length of 1. So we can use then our area for a equilateral triangle, 1 squared square root 3 over 4. So after canceling the 2's, we get 3 root 3 over 2. And that is going to be our final answer then in this case. The area of this region S is 3/2 root 3, or answer choice C. Okay. that will do it for this week's video. Stay tuned for some new problems next week. If you have ideas for upcoming videos or new topics, please let us know in the comments below. Thank you all for watching. I'll see you all next week. Goodbye.